This is my real analysis final exam review problems and solutions video. The topic is the basics of topology on metric spaces. That ends up being like a final exam that you would get in an introductory real analysis course like out of this book by Russell Gordon. However, it's more like exam 1 if you're taking real analysis out of Baby Rudin. Either way, I hope it's useful for you. We start with some definitions, move on to some theorem statements, and then we do some proofs. So start with a bunch of definitions. Complete the following definitions. Note that given a metric space x comma d, so x is the space, which is a non-empty set, d is called a metric, a point little x in capital X and a positive real number, r, you may use this notation effectively, b of x comma r, to denote the open ball of radius r centered at x. This is the more official notation to specify what the metric is, d. This is the set of all points little y in capital X, the metric space, satisfying the property that the distance between x and y is less than r. We literally imagine this as an open ball, maybe a disk in 2 dimensions or a actual ball in 3 dimensions, but you also need to realize this applies to abstract metric spaces. Part A says, again, let x comma d be a metric space, so that is again a non-empty set equipped with the metric, d. Let E be a subset of x, and let little x be an element of capital X. Define, this is a definition, what it means for x to be an interior point of E. Here's the intuition. I do want to draw some pictures, but you need to also be able to give these definitions without pictures. We can imagine like the plane being the metric space that we're talking about. We can imagine the set E as maybe being some sort of blob in the plane. Maybe it contains its boundary, maybe it doesn't, or maybe it contains part of its boundary and maybe not another part. We're wondering what it means for a point x to be an interior point of this set E. Intuitively, we don't want it to be on the boundary. We want it to be some small distance away from the boundary. What does that mean? How do you make that precise? It means there's some open ball centered at the point, possibly very small if the point is close to the boundary, that is entirely inside the set E. Okay, so that effectively is going to be the definition. The picture helps you understand the definition, but the key thing is you want to be able to define these things without pictures, purely with symbols. I'm also going to introduce notation that we're going to use in some other problems here. To say that x is an interior point of E means that x is in the set E superscript circle. What is that circle? Is it the degree symbol or something? No, it's just notation that refers to the interior of E. As a set, it's the set of all interior points. So effectively, by writing x as an element of E circle here, we're saying x is an interior point of E. This is going to be part of my definition, and again, I'm going to use this notation later. X is an interior point of E if what? Again, if we can do this. If there exists some possibly very small positive number r such that the open ball of radius r centered at x is completely inside of E. Such that the open ball, and here I'll use this shorthand notation, centered at x of radius r is entirely inside of E. In this picture, this point, this little green point that I made with this little red open ball about that point, that is an interior point of E. However, a point on the boundary of E is not an interior point, no matter how small of a little open ball you make centered at that point, it's not going to be a subset of E. Likewise, a point outside of E will not be an interior point of E. Okay, so that's what it means to be an interior point. On to the next definition. Continuing in the same theme, we've got a metric space. We want to define what it means for a subset E of the metric space to be open in X. An open set is another way you could say that. Define that. There are a few different ways it could be done. Quickest way to define this, if you've already defined the interior of E to be the set of all interior points of E, you can say that E is open in X. Again, if you've already defined E circle here, the interior of E, if the interior of E equals E. That would be the quickest definition of it. But what does that really mean? And maybe we should define more precisely what that means as our official definition. This would be the quickest definition if the interior of E has been defined as the set of all interior points of E. Okay. More officially, E is open in X if every point of E is an interior point of E. If every point of E is an interior point of E. Intuitively, what this means is E is not like this set. E does not include some of its boundary points. Okay? All the points of E are interior points. If this were E, these points on the boundary of E would not be interior points of E. Therefore, there would be some points of E that are not interior points of E, and E would not be open. Likewise, if we included the entire boundary of E, it would not be an open set. When we're thinking about these pictures that are two-dimensional pictures, we need the entire boundary of E to not be a part of E. Again, E is everything inside here. In this picture, including the boundary. In this picture, not including the boundary. Now all the points in E are in fact interior points of E. And we can say that E is an open set. Okay? These pictures are helpful, but they're not the end-all be-all of understanding open and ultimately closed sets. They're helpful, but you really need to go back to the definition ultimately. That's what it means to be open. Next definition. Let X comma D be a metric space, and let E be a subset of X. Define, once again a definition, what it means for X to be what's called a limit point of E. Okay, let's do the intuition right away here as well. Should have done it, I think, in the second one too. E can be any old set, but this is easiest to think about if you imagine E to be a sequence of points. So here we got some points in the plane, sort of moving around here. And imagine this sequence of points does consist of points that get closer and closer together as we keep going, effectively having a limit at some point in the plane, but never maybe equaling that limit. Say they're approaching this point right here, for example. If that's the case, then intuitively we would want that point, that red dot right there, to be a limit point of this set E. Okay? It is a limiting value, you might say, of that sequence of points. We would also want it to be a limit point. We would also want, if the sequence maybe bounced back and forth, here, then here, then here, then here, then here, then here, etc., and approached, say, two different points in a sense. Technically speaking, having two distinct subsequences that are convergent, we would also want both of those points to be limit points of that set E. Okay? So that's the intuition in a special case for what you would intuitively want to be limit points. But again, this definition applies more generally. E doesn't have to be a sequence or the outputs of a sequence. It can be any subset of the metric space X. But what would we want for a limit point? We would want, given any open ball at a point we want to be a limit point, no matter how small, there should be elements of E inside that open ball that are not necessarily equal to the point itself, distinct from the point itself. X is a limit point of E. Notationally written, X is an E prime. E prime is the set of all limit points of E. It is often called the derived set. Set of all limit points of E. Is it a derivative? Is it like calculus? No. Okay. Well, at least not in the most basic sense. The derived set X is a limit point of E if what? If for all open balls, no matter how small, for all positive radii, no matter how small, you could say there exists a point in the open ball centered at X of that radius other than X itself. That could be written more compactly as the intersection of E, there exists a point in E, with the open ball, take away X. So this is the open ball centered at X of radius R, take away the point X, take away the center of the open ball, if that is non-empty. There's some point, call it Y, in that open ball that's not equal to X, and also Y is in E. Okay? No matter how small this little red circle is centered at this point that's going to be a limit point, there's some green point in that set that's not the red point. Is the red point part of E or not? I haven't said. The red point might be part of E. The red point might not be part of E. By the way, interior points of a given set are part of the set. By definition, the fact that the open ball does contain X will mean all interior points of a set are in the set. E circle, the interior of E, is always a subset of E itself. When E is open, it also goes the other direction. Any element of E is an interior point of E. This is what a limit point is. That's going to be related to the next definition. Suppose we've got a metric space, and once again a subset K of X. Define what it means for K to be closed in X. There are a few ways this can be done. The official definition is K is closed in X if what? If every limit point of K is in fact an element of K. If every limit point of K is an element of K. That's the official definition of being closed in X. Notationally, you could write that the derived set K prime, I don't know why I switched to a K here instead of an E, I guess that's a common letter to use for closed sets, is a subset of K. That's another way you could define it. Some people define closed sets differently, though, in a way that's not immediately obviously equivalent. Alternatively, K is closed in X. K is closed in X if its complement, X take away K, is open in X. Now, technically speaking, you do need to do some work to show these definitions are equivalent to each other. That takes work. That takes proof. Some people, most people, probably define closed sets this way. Some define this closed sets this way. Either way you think about it, intuitively, if you're imagining your sets as being blobs, the set is going to be closed if it does contain its boundary intuitively. That's one kind of example to think about. It's not the only kind of example to think about. Every limit point of K is an element of K. What are the limit points of such a set like this? They are all the points that you see shaded, including the boundary. And by drawing the boundary bold, I've emphasized that it is part of K. That is a limited view of closed sets, though. You should also think about other kinds of examples, like these examples up here. These, whether it's a sequence of points E or a sequence of points that bounces back and forth, two sort of sequences with two different subsequences that are convergent, for example. If those red dots, which are limit points of E, are not part of E, then by definition E will not be closed. But if they are part of E, if I include those red dots that are the limit points of these sequences as part of my definition of E, then E would be closed. Also, finite sets are closed. There's a set with 4 points here. K represents those 4 points. Those are closed sets as well, but trivially so. Why? Because finite sets have no limit points. None of these points, these 4 points, is a limit point of the set K. Think about the definition of a limit point. Given any open ball of radius r, no matter how small r is, there's got to be something both in E and in the open ball that's not equal to x. There are plenty of open balls around any of these points that do not include other points of K besides the point they're centered at, that they're centered at. So they're not limit points. And therefore, trivially speaking, finite sets are closed because they don't have any limit points. Every limit point of K is an element of K because there are no limit points of K. So they're closed in a trivial way. In both of these pictures, the complement is definitely open. Everything outside of this K would be a set outside here, would not include that boundary, would be an open set. The entire plane, take away these 4 points, would be an open set as well. Think about the definition of an open set. Okay, so that's an alternative definition that you could give. Let me give one more alternative definition related to another concept that I'm going to use later, something called the closure of K, denoted by K bar. By definition, the closure of any set is the union of that set with its derived set, with its set of limit points. And since K is closed in X if the derived set is a subset of K, it turns out, if you think about it, that'll be equivalent to the closure of K being equal to K itself. Certainly K is always a subset of its closure, because K bar, the closure, is the union of K with another set. If K bar is also a subset of K, ultimately, if they're equal, then K will be closed. K is closed if K equals K bar. Okay? K will always be a subset of K bar. If they're actually equal, that's also equivalent to K being closed. That could be another definition of closed set, though again, you have to really prove all these things are equivalent to each other. Next problem, part E. Another definition. These definitions, these next few definitions are leading up to the definition of a compact set, a very fundamental idea. Suppose you got a metric space and a subset. Let cursive G, I guess is what that is, be a collection of subsets of X. So this is just an arbitrary index set. Could be a finite set, could be a countably infinite set, could even be an uncountably infinite set. What is it? It doesn't matter. For each alpha in this set, this is a capital omega, there is some G sub alpha in this collection. Define what it means for this collection to be what's called an open cover of E. This happens if, first of all, each G alpha is open. G alpha is open in X for all alpha in capital omega. That's part of the definition related to the word open. What does it mean to be an open cover of E? Well, what it sounds like. It's like a blanket for E. Here's E, subset, say, of X being maybe the entire plane. If our collection consists of sets that cover E completely, when you think about drawing them, then they form an open cover of E. E is contained in their union. And E is contained in the union of these G alphas. Okay, so those two conditions mean this cursive G, this collection of these G alpha sets, forms an open cover of E. On to page 2. Continuing with some more definitions, again leading up to the definition of a compact set. Then we have some theorem statements, then we have some examples, and then some proofs. Got a metric space again. E is a subset of X again. Cursive G is a collection of sets that is an open cover of E already. Define what it means for G to have a finite subcover of the set E that's implied. Well, it's already an open cover of E. G is a finite subcover of E if some finite subcollection of cursive G also covers E. To be more precise, i.e., if there exists G sub alpha 1, comma G sub alpha 2, comma through, say, G sub alpha n in cursive G, in this collection, such that E is contained in their union. G sub alpha 1 unioned with G sub alpha 2, union, etc. with G sub alpha n. That would be a finite subcover. We're already assuming cursive G, this collection, is an open cover of E. It's got a finite subcover if that condition is holds. Kind of weird definitions leading up to this definition of what it means for a set E to be compact in a metric space. E is compact if every open cover of E contains a finite subcover. Of E. Okay, a very short definition, a very strange definition. How in the world is this something relevant? Why is this important? That's not clear at all. We're going to do some proofs related to these ideas later that do hit on why they are important. It's related to things like continuity and some important theorems related to continuity of functions, like, for example, the Extreme Value Theorem, a very important theorem in math. We can understand this in the context of Euclidean space through something called the Heine-Borel Theorem, which is the next problem, is to state that theorem. State the Heine-Borel Theorem. It gives an equivalent definition of what a compact set is, though it does use a definition, a term that I haven't defined yet, though I will allude to its definition. Let X be Euclidean space. Some Rn, say, and D, the metric, be the standard metric D sub 2. This is the Euclidean metric. What is the Euclidean metric? D2, the distance sub 2 between 2 points x and y in Rn, is what you get from the Pythagorean theorem, effectively. It's the distance formula. It's the square root of the sum, I goes from 1 to n, of the squares of the differences between the components or the coordinates of x and y individually. Call them x sub I and y sub I. Take those differences, square them, add them up, take the square root. That's called the Euclidean metric. The 2 here refers to the fact that we're squaring and taking a square root. You can have other kinds of metrics as well. In Euclidean space, other kind of metrics give you what are called equivalent topologies, so it's not a real big deal, but the book I use states it in terms of the ordinary Euclidean metric. Ordinary Euclidean metric of measuring distances. Then E, a subset of X, is compact in X in this metric space, which you could also denote by X comma D to emphasize there's both a non-empty set, a space, and a metric. Compact in X by this definition, if and only if E is closed. We already defined what closed means. It contains all its limit points. And bounded in X. I haven't said what bounded means, but I hope it's pretty intuitive. It's got finite extent in space. It doesn't go off to infinity in some direction. Technically, the definition of what it means for E to be bounded in X is it's contained in some open ball. That's a good enough definition of bounded. Closed, again, it contains all its limit points. So being compact in Euclidean space is equivalent to being closed and bounded, and being closed and bounded is easier to visualize, easier to imagine. But the official definition of compact is up here, and that applies even when you can't visualize things. Part B. Suppose we've got two metric spaces, x comma d, so x is the space, d is the metric, and y comma rho, y is another space, and rho is a metric on that. I haven't said properties that metrics have to hold. I'm assuming you know that. And let f be a function whose domain is x and whose codomain is y. The target space is y. State a theorem that gives an equivalent condition for f to be continuous on all of x, a continuous map, we say for short, in terms of certain preimages. And also give the epsilon delta definition of continuity first. Okay, so I got a couple things going on here in this problem. All right, this is a pretty important thing here. It's a theorem when you're talking about the theory of metric spaces that ultimately justifies the abstract definition of what's called a topological space. This is what this is hinting at. That's why it's important. It's a theorem here. It's really more of a definition, an axiom for topological spaces. But what is, first of all, the epsilon delta definition of continuity first? Okay. F from x to y is continuous on x if what? First of all, if it's continuous at each point of x. For all, say, little x sub 0 in capital X, we have the epsilon delta definition. For all such points, and for all epsilon greater than 0, there exists a delta greater than 0 such that something happens. Now, when you're dealing with, say, the real number line, this is typically written in terms of absolute values. If when x is close enough to x0, if the absolute value of x minus x0 is less than delta, then f of x and f of x0 will be close together as well. They'll be within epsilon of each other. I could write that in terms of the metrics like this. The distance between x and x0 being less than delta, that metric expression is analogous to the absolute value of x minus x0 when we're talking about the metric space being the real line. D is the metric on x, though, so that's why I need to use the D there. But that implies now rho is the metric on y. I've got to use rho to measure the distances between f of x and f of x0. That is going to be less than epsilon. You can also state this in terms of open balls. For all x0 in x, and for all epsilon greater than 0, there exists a delta greater than 0 such that if little x is in the open ball with respect to the matrix D, centered at x and radius delta implies that f of x is in the open ball in the other metric space with respect to the metric rho, centered at f of x0 and having radius epsilon. That would be an alternative way to write that. For me, my students, either way is okay to write that. That's just the definition first. Now what is the theorem? The theorem now, let's call this condition A. Is there going to be a B? Well, sort of, but I'm not going to label it with a B. Maybe I should just label it with a C for condition here. C. F from x to y is continuous on X according to condition C if and only if continuous in terms of certain preimages, inverse images they're called. Here it is. For all open sets, call them U, in the target space, the codomain Y, the preimage F inverse of U, which exists even if F is not one-to-one. You can still define this set. This is the set of all points in capital X that get mapped into U. For all open sets U and Y, this preimage is open in X. Okay? That's a theorem that takes proof. And in fact, we are going to prove one direction of this theorem. I think the left to right definition, or fact, implication here, later in this video here. So it takes proof, but this theorem becomes, again, the basis for the axiomatic approach to topology, point set topology. This part here essentially becomes the definition of continuity of a map in abstract topology. Because in abstract topology, you do want to develop it without reference to metrics. I mean, metric spaces are important examples of topological spaces, but there are some topological spaces that are not metric spaces, so you do want to have a definition of continuity purely in terms of open sets, and it turns out, because of this theorem, that the preimage idea is the key idea. For every open set in Y, the preimage of that open set is open in X. That's equivalent to being continuous on X. Last statement here, and then we get to some examples and then to the proofs. State a partial generalization of the extreme value theorem to metric spaces. I'll get you started. Let X comma D and Y comma rho be metric spaces. Let lil f be a continuous map, continuous on all of X. Let K be a subset of X. Be what? What's the extreme value theorem in calculus? Got a continuous function defined in a closed and bounded interval. Hey, a compact set is going to have a maximum and a minimum value. Effectively, that is implied by the direct image also being compact. Not equivalent, but effectively a consequence of that. If it's continuous on X, let K be a compact set in X. In X, that's the word set there, in X. The conclusion is then the direct image, f of K, which is the set of all outputs of F, as the input X ranges over K, is compact in Y, according to the definition of compact in terms of open covers and finite subcovers that we talked about. Okay? We're not saying these are Euclidean spaces, so the Heine-Borel theorem doesn't apply, though we could imagine them to be Euclidean spaces, and then the Heine-Borel theorem would apply. Okay? And if X and Y, in fact, are both the real line, then you can think of this in terms of the ordinary extreme value theorem, and I'll let you think about that. You'll have to think about being closed and bounded and what that would mean in that context. There's also a generalization of the intermediate value theorem, which I'm not going to get into, which is related to the concept of connectedness. I don't want to take the time to get into connectedness, but you can look into that if you want. Next page. Examples that are related to interiors, derived sets, and closures. Consider each set E below. Identify the interior, E circle. Again, is that a degree symbol? No, I'll just say E circle, or just the interior. The closure. Not asked to identify E prime, the derived set. I think I will anyway. Little bonus here. So identify those sets. Then for each case, identify whether E is open, closed, both, or neither. Evidently, there are sets that are both open and closed. Weird. Or neither open nor closed. Actually, I drew a picture of a set that was neither before. Also identify whether E is compact or not. These sets are all subsets of Euclidean space, so we can really just think about whether these sets are closed and bounded. So this first set, E, is on the real number line, the interval from 4 to 6, not including 4, but including 6. Okay. What's its interior? Set of all interior points, points that are interior points of this set, points that have some open ball centered at them. Open ball in one dimension, there's going to be a little open interval that's entirely inside the set. That's going to be all the points between 4 and 6, not equal to 4, also not equal to 6. It's going to be the open interval from 4 to 6. That'll be the interior. It doesn't include 6, and 6 is not an interior point of this set. There's no little open interval centered at 6 that's going to be entirely inside the set. This is E here. Not including 4, but including 6. What's the derived set? Again, that's not asked for here, but I'll do it anyway. What are the set of all limit points of this set? Certainly each point in E itself is a limit point of E. Think about that. For any point in E, take a little open interval centered at E. There's going to be points inside of E other than the center of that open interval. 4, though, the number 4 is also in the derived set. It's also a limit point of E, even though it's not in E. Any little open interval centered at 4 is going to contain points in E. And 4 itself is not in E. So it's the entire closed interval. The closure then, remember by definition, is the union of E with its derived set, and that's going to be the same as the derived set in this case. Not always, but in this case. That'll be the closure. E is going to be open if it equals its interior. It doesn't, so it's not open. It'll be closed if it equals its closure. It doesn't, so it's not closed. E is neither open nor closed. Is it compact or not? Well, it's not closed. By the Heine-Borel theorem, that means it's not compact. It is bounded, but it's not closed. E is not compact. E is neither open nor closed. E is not compact. Next problem. E is the closed interval from negative 7 to 5. Its interior would be the open interval from negative 7 to 5. Its derived set would be the closed interval from negative 7 to 5. And its closure would be E union E prime is also the closed interval from negative 7 to 5. E does not equal its interior, so it's not open. It does equal its closure, so it is closed. E is closed, but not open. Is it okay to just say closed? Well, you really should say closed but not open, because there are some sets that are both. We will get to that. It is closed. It's also bounded. Therefore, by the Heine-Borel theorem, it's compact. E is compact. C. E is a finite set. 1, 2, 3. What's its interior? Its interior is the empty set. There's no interior points of a finite set. No point you could think of is going to be an interior point of that. Its derived set is also empty. I mentioned that before as well when I drew some pictures. Any finite set is going to have an empty derived set. There are going to be no limit points of any finite set. Its closure, however, is not empty because its closure by definition is E union E prime. That is going to be E itself. 1, 2, 3. Okay? E does not equal its interior, so it's not open. It does equal its closure, so it is closed. E is closed, but not open. Is it compact? Is it closed and bounded? Certainly, E is compact. The word compact in English sort of has connotations of just small, which this certainly is. This one's compact though too, and it's not bounded, and it's closed. However, this one, so that one was compact. This one's not compact, even though it's small, so to speak. It's not bound. It is bounded. It's not compact though, so you don't take the word compact's connotation in everyday life too seriously here. D equals E equals all of the real line. What are the interior points of the entire real line? They are the entire real line. Every point in the entire real line is an interior point of the entire real line. What are its limit points? The entire real line. Therefore, what's its closure? The entire real line. They're all equal to R. E does equal its interior, so it's open. It also equals its closure, so it's also closed. E is both open and closed. And in the standard topology of the real line, which the standard metric generates, which is the absolute value of x minus y, the only two sets that are both open and closed are the entire real line and also the empty set, its complement. Is it compact? No. It is closed, but it's not bounded. Part E. E is the set of all points 1 over n, so this would be 1, 1/2, 1/3, 1/4, etc. Not 0. 0 is the limit point of this, but it's not included in the set. I hope it's pretty clear that its interior is actually empty. How about the derived set? What are the set of limit points? I hope that's fairly clear to be just the number 0. The closure is E union with E prime, so that's going to be the set of all numbers 1 over n as n ranges over the positive integers, the natural numbers, unioned with 0. That's a 0 there. E does not equal its interior, so it's not open. It also does not equal its closure, so it's not closed. E is neither open nor closed. If we had decided to include 0 as an element of E, then it would be closed. But we did not. Since it's not closed, it's not compact. E is not compact. Finally, we've got a two-dimensional example. This is the unit disk in the plane, set of all points such that x squared plus y squared is less than 1. Everything inside the unit circle, and just for kicks, adding on the point 1, 0 relative to the plane here. The interior of E is just this part, all the points satisfying the inequality. If that's true, the derived set will be, think about it here, what are all the possible limit points? Their entire closed disk will be limit points. So change that inequality to a less than or equal to. The closure being E union E prime, and since E is a subset of E prime, is going to equal E prime. Is going to equal this set here. E does not equal its interior because there's this extra point there. If that extra point were not in the set, then it would equal its interior and it would be open. But it does not equal its interior because of that one point there. So it's not open. It does not equal E bar, so it's not closed. E is neither open nor closed. Since it's not closed, it's also not compact. E is not compact. If I was considering the closed unit disk, including the boundary, that would be a set that equals its closure. it would be closed, and it's also bounded. It would be closed and bounded, so it would be compact. On to your favorite part, the proofs. Am I kidding or not? Is it your favorite part or not? I don't know. I don't know who you are. A new kind of idea in this problem, the idea of a norm. Norms are related to metrics. They in fact generate metrics. Let A and B be real numbers with A less than B. Consider this set C of A, B. That's standard notation for the collection of all functions from the closed interval from A to B that are real valued, that are continuous on the entire interval from A to B. That's standard notation. Let the norm, the infinity norm it's called, of a function f in this collection C of AB, these are functions, be the supremum of the set of all possible absolute values of outputs as x ranges over the domain. Note that no matter what the function f is in this collection of continuous functions defined in the closed interval from A to B, such a norm will have a value less than infinity. In other words, it'll be a real number. This set of absolute values of f of x will be bounded above by some real number because of the extreme value theorem in calculus for continuous functions. Prove the triangle inequality. This is true for all functions f and g in this space of continuous functions from A to B. Let me remark, is this a metric space? When I assign this norm, yes it is. You could call it the infinity metric. The distance between two functions in this metric space would be defined by the norm of their difference with respect to that norm, the infinity norm. Okay, that would define a metric. That's just a side note. Is a metric on this space, C, A, B, making it a metric space. And there is a triangle inequality that would follow from this triangle inequality for metrics that we could prove as well. Excuse me. All right, start the proof. Usually when you do proofs, you probably need some scratch work. I'm going to just try to jump into the full proof here. By definition, the norm of f plus g is the supremum, least upper bound, of the set of numbers that are the absolute value of the outputs of this function, f plus g of x, and those outputs are f of x plus g of x, as x ranges over the interval from A to B, the closed and bounded interval from A to B, the compact interval. That's the definition. And that will be a finite number when f and g are in here. Let f and g be elements of this set. Elements are functions here. Supremum is least upper bound. What's my goal? My goal is to show that supremum is less than or equal to the sum of these two numbers. In other words, I'd be done if I can show the sum of these two numbers is an upper bound for this set right here. Okay, so towards that end, let's let, say, alpha be the sup norm of f, the infinity norm, and beta be the sup or infinity norm of g. These are both finite numbers. Our goal is to show the sum alpha plus beta is an upper bound of the set that I'm taking the sup of. By the way, I am allowed to use the triangle inequality for real numbers. hope it's a little hint that we are going to need it. So how do you show it's an upper bound? Giving an arbitrary element in the set, show it's less than or equal to alpha plus beta. You will need the ordinary triangle inequality, and it'll be actually a pretty easy proof. Let x be an arbitrary element of the closed interval from a to b. Then, by the ordinary triangle inequality, or if you want to be more precise, the triangle inequality on the metric space x equals the real numbers, where the metric d is defined by d of x comma y equals the absolute value of x minus y. On R, d is understood, the absolute value of f of x plus g of x is less than or equal to the absolute value of f of x plus the absolute value of g of x. Why is this goal enough? Again, the supremum of this set is the least upper bound. So if I can show alpha plus beta is an upper bound of the set, then the sup of the set will be less than alpha plus beta, because it's the least upper bound. But wait a minute. The absolute value of f of x is definitely less than or equal to alpha, and the absolute value of g of x is definitely less than or equal to beta. So for an arbitrary x in the interval, I've shown that the absolute value of f of x plus g of x is less than or equal to alpha plus beta. Since x is arbitrary, therefore alpha plus beta is an upper bound of the set, because I've shown it's greater than or equal to an arbitrary element of the set. And that's what I wanted to do. I'm essentially done. Therefore, the least upper bound must be less than or equal to the given upper bound. Sup of this set is less than or equal to this upper bound, which is the norm of f plus the norm of g. Okay? So I did that for two arbitrary f and g in C of AB. I'm done. Number 5. Let x comma d be a metric space and let little x be an element of capital X. Carefully and thoroughly prove that the open ball of radius 1, that thing, is also an open set in X by using the definition of an open set being that every point in the set is an interior point of the set, as we saw. Weird. Open. Well, I mean, isn't it true by definition? It's an open ball. This is the set of all y in capital X whose distance to x is less than 1. Isn't that an open set by definition? No, even though we're calling it an open ball, it still takes proof to show it's an open set. Let's draw a picture to imagine the situation here. So there's x. Here's an open ball. I'm pretending capital X is the plane, say, and this distance is 1 unit here. That's our open ball of radius 1, centered at x. Why is it an open set? I need to prove every point in the set is an interior point of the set, no matter how close it is to the boundary. Call that point y. Can I find an open ball centered at y that's contained entirely inside this open ball here? B dx1. The closer y is to the boundary, the smaller the radius of the open ball I need is going to be. How small should it be? The distance between x and y is some number less than 1. I want to make the distance that I use for the open ball centered at y, if you think about it carefully, less than 1 minus the distance between x and y. So let's start the proof. Trying to show that every point in the open ball is an interior point of the open ball. Let y be an arbitrary point in the open ball. It's in the open ball, so its distance to x is less than 1. Our goal is to show y is an interior point of the open ball, which means we want to show there exists a radius, positive radius r, such that the open ball centered at y of radius r is entirely contained inside the open ball of radius 1 centered at x. That'll mean y is an interior point of the open ball of radius 1 centered at x, which will, since y is arbitrary, mean every point in that open ball is an interior point of it, which will mean it's open, as an open set. We think that any positive number smaller than that will work. How about take that difference over 2? That is positive since the distance between x and y is less than 1. Our claim, at least it's a claim that we hope is true, is that the open ball, with respect to this metric, of radius r centered at y is in fact a subset of the original open ball of radius 1 centered at x. And if we can prove that, then we'll be done. So to prove this claim, I need yet another symbol. Say let z be an element of the open ball of radius r centered at y. I've got to show it's in the open ball of radius 1 centered at x. Wow, it sounds like we're going in circles, but that's what we need to do. So I got to think about the distance between x and z. Almost always in these situations, you want to have a light bulb that goes off in your mind saying triangle inequality, triangle inequality. For metrics, here this was a triangle inequality for norms up here. There's a triangle inequality for metrics here when you've got 3 elements, x, y, and z in the metric space. You can say, well, then by the triangle inequality, for metric spaces, if you want extra emphasis here, for any metric space, the distance between x and z is going to be less than or equal to the distance between x and y plus the distance between y and z. At this point, I ended up making a mistake. I said that was less than 1 right away. That led to problems. I'm trying to fix my mistake now. The way to fix the mistake is do not say right away that this is less than 1, as I was tempted to do by this fact, but instead emphasize the fact that the distance between y and z is less than r. So this becomes less than the distance between x and y plus r. But what is r? R is up here. Make that replacement. 1/2 minus 1/2 times the distance between x and y. Simplify that. That simplifies to 1/2 times the distance between x and y plus 1/2. Now use the fact that I'm assuming the distance between x and y is less than 1. This is less than 1/2 times 1 plus 1/2 is 1. So we have done what we set out to do. The distance between x and z is ultimately less than 1. And that means z is an element of the open ball of radius 1 centered at x. We're done. On to the next proof. This is one direction of that condition earlier, of the equivalence of the epsilon delta definition of continuity with the condition about preimages. So what are we trying to prove? Again, consider the epsilon delta definition of continuity. F is continuous on x. I wrote this down before. If for all x sub 0 in capital X, and for all epsilon greater than 0, there exists a delta greater than 0 such that if the distance between x and x0 is less than delta, if x is in this open ball, that implies f of x, the output, is within epsilon of f of x0. It's in this open ball. And the preimage condition, which is what I wrote down for the theorem, f is continuous on x if for every open set u and y, the preimage f inverse of u, which exists even if f is not invertible, even if f is not 1-to-1, is open in x. Prove that A implies B. It is also true that B implies A. So my goal is trying to show this preimage is open in x when u is assumed to be open in y. So start by assuming u is open in y. Let u subset of y be open in y. We want to prove the preimage is open in x. What does that mean? It means every point of the preimages is an interior point of the preimage. Let x sub 0, say, be an element of the preimage. I want to find an open ball of some radius centered at x that's entirely inside the preimage. I'm going to use condition A. I'm assuming condition A is true. I'm trying to show that that implies condition B is true. Okay? This means, well, think about what that means. This means that f of x0 is in U, because that's what it means to be in the preimage. Okay, this is kind of follow your nose kind of stuff here. F of x0 is in U is open in Y, so there must, f of x0 must be an interior point of U. There must be some open ball of a certain radius centered at f of x0 that's entirely inside U. What should we use for the radius of the open ball? How about epsilon? There exists an epsilon greater than 0 such that the open ball of radius epsilon centered at f of x0 is a subset of U. Open ball with respect to the rho metric, b sub rho, centered at f of x0 with radius epsilon is a subset of U. Now I've set myself up to use condition A. Condition A, which I'm assuming is true, I'm also assuming f is continuous on x. On all of x, so in particular at x0. What do these things imply? Think about condition A. It means there exists a delta greater than 0 such that this implication holds for any point in the open ball of radius delta centered at x0. F of x will be in this open ball. So we can say, we can just go ahead and write that down. X being in this open ball implies f of x is in this open ball. Well, what do we think is going to happen? I hope it's intuitive that delta is going to be the radius of the ball that we need to show that's going to be a subset of this thing. Drawing a picture might be helpful. There's x. There's y. X has metric d. Y has metric rho. F is a continuous map from x to y under the epsilon delta definition of continuity. I'm trying to show that it fits the preimage equivalent condition for continuity. I've got a subset U that's open in Y. I'm purposely drawing it without a boundary just to emphasize it's open. I want to show the preimage of that set over here is open in X. Give me an arbitrary X0 in that preimage. Its image under F is going to be over here in U. By definition of what it means to be in the preimage. U is open, so there's some open ball of a certain radius. The radius here is epsilon. That's entirely inside U. The condition A for continuity, the epsilon delta definition, means there's a delta, so that if x is within delta of x0, f of x will be within epsilon of f of x, 0. Forgot my 0 there, sorry. Claiming that delta will be a radius that will work, that this open ball will be a subset of that preimage. That's our claim here. And it's essentially this implication that proves the claim. Open ball of radius delta centered at x0 is a subset of the preimage. F inverse of U. And if we can prove the claim, we'll be done. And again, this implication essentially does it for you. Let X be an element of this open ball. I want to show it's in the preimage. Then by this condition, f of x is in this open ball. But that open ball is a subset of U. So we need that condition as well. Therefore, that means this open ball is a subset of the preimage. And since x0 was an arbitrary element of the preimage, and I've shown that it's an interior point, x0 is an interior point of U, of the preimage. It's an arbitrary point of the preimage that I've shown is also an interior point of the preimage, and therefore the preimage is open. Okay? Again, it feels like you're going around in circles with this stuff, but you really are proving what you need to prove. Last problem. An important problem. We are trying to focus on the most fundamental things here. Let x comma d and y comma rho be metric spaces. Let f be a function from x to y that's continuous on x for all x. All little x in capital X. Let k in capital X be compact in X. Prove its direct image, f of k, the set of all outputs, is compact in Y. I hinted at this problem, this fact earlier. It's a generalization of the extreme value theorem. So what do we have to do? We're not talking Euclidean spaces here, so we cannot apply the Heine-Borel theorem, though if we did, that might not necessarily be much help unless you could apply the Euclidean version of the extreme value theorem. We need the definition of compact in terms of every open cover having a finite subcover. That's what we need. Picture, once again, is not a proof, but it's probably helpful. Here's X. F is a continuous map on all of X into Y. K is a compact subset of X. I'll draw it to include its boundary, thinking about that Heine-Borel theorem as analogous. It's closed and bounded, so to speak, if this were a subset of Euclidean space. Here's f of k, the direct image, not the preimage. We want to prove that if k is compact in X, then f of k is compact in Y. So strategize. Think about the definition of compactness. Give me an arbitrary open cover of the thing I'm trying to prove is compact, which in general will have infinitely many sets in the collection. Show that it's got a finite subcover. Got to use the fact that f is continuous and k is compact. How do you do that? continuity, we can use the preimage condition, perhaps. Take the preimage of all these sets. They hopefully will form an open cover of K. And since K is compact, there will be a finite subcover. And take those finitely many preimages and hopefully the corresponding finitely many U's over here will be an open cover, a subcover of f of K of the original collection. That's either easy or hard depending on how experienced you are with this. Proof. Suppose you got an open cover of the direct image. A general open cover. U sub alpha, as alpha varies over some index subset omega, which in general could be an infinite set, could be countably infinite, could even be uncountably infinite, be an open cover of the direct image f of K. I could call this cursive G if I like. We want to show it's got a finite subcover, and then we'll be done. Therefore, U alpha, by definition of an open cover, is open in Y for all alpha in capital omega, because that's what an open cover means in part. I'll also say what else it means. F of K is contained in the union of all the U alphas as alpha ranges over the index set capital omega. That's what it means to be an open cover. Yeah, by the fact that we just talked about, F is continuous on X implies that the collection of preimages, well, or each preimage of each of these U alphas is open in X. F inverse, which again, of U alpha, which again exists whether F is invertible or not, is open in X for all alpha in capital omega. We claim that the collection of all such preimages forms an open cover of K. They're certainly all open sets. Do they cover K? Claim K is a subset of the union of these preimages. How do you prove the claim? Let little x be an arbitrary element of K. I want to show it's in the union. You got to use the things this is set up to use. If x is in K, then f of x is in f of K by definition. Got to use the fact that that direct image is compact. I got to use it. And therefore, by this condition here, f of x is in the union of the U alphas. And therefore, that implies there exists some particular alpha in capital omega. Maybe I should call it alpha star to say it's special, such that f of x is in U alpha star. If it's in the union, it's in at least one set. Going around the horn here, that means x itself must be in the preimage of U alpha star. X is in the preimage of U sub alpha star. And that implies x is in the union of all the preimages. If you're in one preimage, you are in the union of all of them. And the claim is proved. Therefore, the collection G star of all preimages of all the U alphas is an open cover of K. I get to use the fact that K is compact. Take it step by step. I want to use the fact that K is compact. I'm assuming that. K being compact implies there exists a finite subcover of G star. I could label the sets in the final subcover F inverse, the preimage of U sub alpha 1, preimage of U sub alpha 2, etc. that are all open sets, and K is contained in their union. K is a subset of F inverse of U sub alpha 1, union with, I should really say, the preimage of U sub alpha 2, etc., through the preimage of U sub alpha n. What do you hope is going to happen? What's another claim that will finish the problem? You hope the U alphas without the preimage symbol forms a finite subcover of F of K. The direct image that we're trying to show is compact. Claim K is contained in the union of the U's, this finite union. In other words, these U's form a finite subcover of F of K, of the original open cover. It's got to be with respect to the original open cover. These U's are in the original open cover, which they are by how I've constructed this. And how do you prove that claim, which will finish the problem? It's not too hard. Let Y be an F of capital K. That implies there exists an X in capital K such that Y equals little f of little x. But X is also in this union of these preimages. So exists an X in the union of those preimages. Such that Y equals f of x. I could have put that x was in the preimages right away, the union. And what does that mean? X is in one of these preimages. It's because it's in the union. So f of x is going to be in one of the U's, but Y equals f of x. To be extra picky about it, so there exists an M from 1 to n such that x is in the preimage of U sub alpha m. Therefore, Y equals f of x is in U sub alpha m for some m from 1 to n. And that essentially proves the claim, because Y was in the direct image. It's an element of this set. And I've just shown it's in one of these, and therefore it's in their union. Therefore, Y is in the union of this finite subcollection of open sets that really then is a finite open subcover of the original open cover of F of capital K. And that proves F of capital K, that direct image, is compact. In the metric space capital Y. Again, very confusing for the uninitiated. Like we're going around and around in circles. The theory, in a sense, is like it's just like set up to make it work. And it justifies the weird definition of compactness in terms of every open cover having a finite subcover because it makes the proof work. That's why that definition is made, to make this theorem true. And this theorem really is a partial generalization of the extreme value theorem, and therefore it's important. It's something to get used to, something to keep working at. Thanks for watching.